All right, so I'm going to be talking about what are called Lie group integrators, and the basic idea behind Lie group integrators are that they are numerical methods which are constructed in such a way that they automatically stay on a nonlinear manifold, which is a Lie group. Okay, so Lie group integrators. And before we go too far into this, I'm going to briefly remind you of the definition of a Lie group and the associated Lie algebras. Okay, so definition. So a Lie group, let's call it G, right, is a differentiable manifold which is equipped with a product that's denoted by just a dot, okay, which is mapped from two copies of the group to the group itself, okay, and it satisfies some properties. Following properties. So the first one is that, as the name implies, it's like this product. It's like makes this set G a group. So it has to be that this product has the property that's associative. So associativity, which basically says that if you take P and you product it with the product of Q and R, right, that is, this is equal to the product of P and Q, which is then producted with R. Okay, so more or less what that means is that it's like when you have sort of, say, a triple product like this, then it doesn't matter which of the products you take first. Okay, and this has to be true for all P, Q, and R in the group. The second property is that there has to be an identity element. Okay, so what that means is that there exists an element which I'm going to denote by 1, because most of the Lie groups we're going to be working with are matrix Lie groups where the identity is denoted by this sort of boldface 1. Okay, so if you have 1 in this group with the property, the identity in this group such that the identity times any group element is equal to the group element times the identity is equal to that group element itself, and this is true for all group elements. Okay, and then once you have an identity element, then you can start talking about inverses. Okay, so that means for all elements of the group, all P in the group, right, there exists something which we denote by P inverse in the group with the property that P product with P inverse is the product of P inverse with P is the identity. Okay. All right. So that's all right. So these, of course, are just the sort of the axiomatic properties. It's like a group satisfies, and so basically what a Lie group is a manifold which also has a group structure, but then we want to have that group structure be compatible with the manifold structure in some way, shape, or form, and the way you sort of do this is that there are sort of two maps. It's like which you want to be smooth with respect to the manifold structure. One of the maps is this product itself, and then the other map is the map from the element P, it's like to its inverse. Okay, so the maps, so you want that the maps, you know, P and Q to the product P dot Q, right? This is of course just the product map, right? And the map from P to P inverse, right, are smooth maps with respect to the manifold structure. Okay, so again, this in a nutshell is, it's like it's the sort of definition, if you will, of a Lie group. And so there are, of course, many examples of Lie groups. In fact, there sort of a standard example is the rotation group, right? If you look at the space of all rotation matrices, then the matrix product of matrices, right, satisfies these properties and makes it like the space of rotation matrices a Lie group in the following sense. Okay. All right, so let me just stop here for a minute.